the image that you can see here is what you call a pendulum chronograph or a chronometer. It's the same thing. The the Galton pendulum chronograph was similar to this design. I don't actually think this was his original device. I think this was another device from the 19th century. But what you'll notice from this design is that as the pendulum rotates or pivots along this measurement bar, you're 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 basically measuring the distance that it traveled, and that you can compute into time. So it's not really a timer like you think of a classic timer where you're activating a switch and then you measure the time elapsed. You're really measuring how much distance was traveled, and then you convert that into time. So it's quite a different approach to measuring reaction time, and it was claimed by uh, Dordanova et al. 2013 that they reconstructed a device similar to his, and they found that it has very little intrinsic latency because of the fact that it doesn't really act as a timer. So you don't have to wait for a signal to transmit. You don't have to wait for mechanisms to be actuated. It's a streamlined type of device. And although we don't have an original Galton chronograph, it'd be nice to have one. I can't measure the latency of a Galton chronograph. I've never claimed to have estimated the latency of that device. What I had claimed and what people took objection to was the fact that if you take, and this was my experiment, if you take one of these high FPS webcams like this little guy here, it's 330 FPS. You can also use one of these guys. This is what they call a machine vision camera. These are very high speed cameras. This actually shoots at 815 FPS. The problem is that when you run it at 815 FPS, the sensor doesn't take enough light, and so you have to do it in the bright daylight, and you can't see the computer monitor. So I bought these thinking I can get higher speeds, but it doesn't take in enough light. So what I've been using is this little webcam right here. And again, that's 330 FPS. And that means if you take 1,000 milliseconds divided by 330, it's 3.3 milliseconds of elapsed time per frame. So if you plug the video that you take into the frame rate analyzer, by definition, one frame is 3.3 milliseconds. You can't really get much more accurate in terms of recording motion than this type of configuration. In fact, when they were building the first nuclear weapons, they were using high-speed rotary cameras where you'd have a big wheel and a bunch of mirrors on each wheel, and you'd rotate the wheel really fast, and you'd be able to capture millions of frames per second. And that's how they recorded the Trinity explosion. And they could calculate how long the explosion actually lasted with a high-speed camera. So if you're talking about sports or measuring, explosions or measuring the bullet traveling through the air, you're going to use a 10,000 frames per second camera. Now, in the case of reaction time, you don't really need to get into the tenth of a millisecond range. You only need a few milliseconds, give or take. And so the existing devices have about 80 milliseconds of latency, and I'm looking at about 3 milliseconds of latency intrinsic to the camera. You could get lower than that. You could buy a camera that had 10,000 frames per second, but it would be kind of superfluous. So when you use this type of device, what you want to have is a pretty big computer screen that you can film, and it doesn't really matter what stimuli you have. You could use a small little stimuli, which is what they use on Inquisite 6, which is a small little red dot, or you could use this stimuli on Human Benchmark, which lights up the whole screen in green from the red background. And then you want to try to capture in the same frame, you want to try to capture your finger, your foot, or some type of body part that you can actuate. You can use your eyelashes if you wanted. I don't know what you could use. Anything that's, as long as you're not paraplegic, you can use your nerve signals to move your muscle. That's really what reaction time is, right? It's the time that it takes for the eyes to absorb photons, and the eyes to send an electrical signal to the brain, and then the brain processes it, which takes up most of the time, and then the nerves conduct the signal to your muscles. And the nerve conduction velocity only accounts for a small fraction of reaction time. Most of it's cognitive processing, which is why these for example, Galton or Jensen argue that it's a form of intelligence, because it is mostly cognitive processing that takes up the whatever 150 milliseconds that it is. So what I objected to was the notion that these modern devices that yield results of somewhere like 240 milliseconds are veracious. I don't think they are, not even close. And so using this method, you're able to get, or at least I am able to get the reaction time down to about 150 milliseconds. In fact, the lowest I've gotten is about 130. And the fastest you can get with this computer test, which is, you can bring it up right here, is human benchmark. The fastest you can get is about 230. And so the running average, I collected about 300 tries. The running average on human benchmark is about 235 on my computer, and then about 150 using this device. And so you compute that, it's about 80 milliseconds of difference. And then what you can do with that number is assume that all of these other experiments use a similar type of setup. Now, you can't be certain, for example, that these studies that Ian Deary performed, which is what they used to compare to Galton's original sample. I don't know what kind of computers they used, but they were computer-based tests. That's all I know. They were not mechanical pendulums like this one right here. They definitely were not mechanical pendulums. So if they're not mechanical pendulums, then you're likely dealing with some type of software-based test. And any kind of software-based test is going to have about 20 milliseconds for the mouse, another 20 milliseconds for the monitor, and then you double that because latency acts both ways. Because it's a bit confusing, but when you click activate, right, it's going to start timing. So when the computer starts registering the point time 0, okay, the monitor begins refreshing, but since the monitor takes 20 milliseconds to refresh, the software program starts calculating time 0 before the monitor refreshes. So you have 20 milliseconds built in on the inside, and then another 20 milliseconds on the outside. So it's going both ways. Latency is acting both ways. That's an important point to understand. So I think the reason actually I'm making this video is because one of these big HBD kings of HBD, Emil Kirkegaard, took issue with it, and he's a bit of a troll, but he seemed to imply that what we're doing is we're doing a population sample. We're not doing a population sample. This has nothing to do with sample size. This is calibration of two different systems, right? So imagine you have two sensors, two speedometers, two tape measures, right? It doesn't matter what you're testing. You're getting the difference between the two measurement instruments. So people didn't quite understand that. There's a lot of grifters in the HBD community who think they know everything and they're good at R or whatever, but they're really not very conceptually minded. And so I'm actually the only one to have performed this experiment using high-speed cameras. Everyone else assumes that you can just use computers to measure reaction time. That's not even close. And then people could argue, well, what about the fact that you have the internet latency, and it has to actually process the signal to the server, which might be located thousands of miles away, and that is true. But interestingly enough, when you run a local-based program like Inquisite, which is based on your PC, it doesn't require the internet to use, you get the same score. In fact, the Inquisite's a bit slower because the Inquisite makes you use the keyboard. It doesn't use a mouse, and it takes time to depress this keyboard or this key. If you use, for example, your laptop, which has a much shorter keystroke, it's going to be about 10 milliseconds faster than on the classic keyboard. So no one takes this into account, and they go around saying that reaction time slowed because the numbers from Galton were faster. But I don't think anybody in the right mind would compare a device like this, which I can't see in the design of this device. I can't see any area that it could actually have any intrinsic latency, because again, it's not a timer. You measure the distance moved and you compute that into time, and it's a completely different beast. And so all of these people don't seem to understand that, and I'm trying to clarify that, because it's important to clarify, because if you're going to make these claims that you have slowing reaction time, you have to isolate latency in these modern systems, and no one's done that. And so I don't know how you would go about doing that other than either recreating that device, which I can't do, and no one else is going to do that either, or just using this clever method, which is much easier and in fact probably even more accurate. Now, the argument goes that, well, yeah, but what if this device had latency, right? Does that still mean modern samples are slower? well, it might have had some latency. No one knows for sure, but the way it's designed definitely suggests that it had a lot less latency. Could have had 20 milliseconds, could have even had 30 milliseconds. If you assume that you have about 150 with this method, and then you have about 185 with the old method, then you could assume that you're dealing with about 30 or so milliseconds of latency. So you could assume that the Galton device had 50 milliseconds of latency, and if that's the case, we've slowed by about 20 milliseconds. That's possible, but I don't know of any studies that have shown that his device did have 20 milliseconds of latency. So you can't go around saying that because I don't have any evidence for it. So the key to understand is this is not a sample experiment. This is a way to isolate measurement fidelity of two different systems. So you could have a day when you're really slow in terms of your reaction time, and the difference would be the same between the two systems. And never thought I'd actually have to explain this, but apparently a lot of these people in the HPD community are a bit of, they're kind of autistic, and they tend to be quantitatively oriented. They tend to be good at mathematics and programming, but you notice that people who are good at mathematics and programming often have very low creativity. They tend to have very weak ability to conceptualize things, and they're not very inventive. They tend to be in the box thinkers. They tend to be bounded thinkers as opposed to out of the box thinkers. And a lot of the people in the HPD community are these sort of uncreative, high IQ kind of programming types. And programming types are just, again, they're not very creative. They don't really come up with new ideas or new concepts. They're kind of like East Asians, they're very quantitative, and that's a problem because the best HBD guys are people like Dutton or Woodley, and these are very verbal people. These are idea, kind of conceptual, theoretical type of brains. But Kierkegaard and his crowd are programming guys, and they just don't really appreciate or understand new concepts, and they can't really acknowledge the fact that you do need to innovate to actually measure reaction. You can't just keep doing the same thing over and over again. And so that's just why I'm making this video, because it does appear that when I was having this interaction, it does appear that these guys are on a different wavelength. Because of that quantitative tilt, they just can't think conceptually. They're only thinking within these very rigid cognitive frameworks. And so I'm more of a conceptual, kind of inventive, creative type guy, more of an artist type. I'm not quantitative. I'm not a programmer or quantitative at all. But I'm decent at coming up with new ideas, and so that's the kind of people that we need to do a lot of theoretical work in HBD, because if you just have these quant types that pull together a bunch of stats, you're really not going to gain much from doing that. You need to actually come up with theory and then prove that theory with experimentation, and none of these guys do that. So. That's the only reason I made this video. I shouldn't have had to make this video. It's disappointing that I have, but it was so disappointing to see that reaction, that the reaction to my reaction time experiment was quite infantile and betokened, I think, a lack of conceptual and theoretical understanding, and I think that's imputable to the very quantitative tilt that you find in a lot of the HBD community. So I think that covers it.